Last month, the world was transfixed by the interstellar comet 3I Atlas, drifting harmlessly past Earth. A story of cosmic wonder that seemed to close without danger. But this week, a far larger object, 100 times the mass of Atlas, is entering Earth's neighborhood, and almost nobody is talking about it. Its name, C2025 R2 Swan. It was invisible to every telescope on Earth until it was already past the sun. Hidden in the glare, it arrived unannounced, untracked, and undiscovered. And in just 7 days, it will sweep closer to Earth than any major comet in recent memory. The question scientists are asking tonight isn't whether it will hit us. It won't. But how such a massive body slipped through the very systems designed to see everything. What else might be coming that we simply can't see? It started quietly, without alarms or breaking news. On September 11th, 2025, astronomer Vladimir Bezugly noticed a faint ultraviolet anomaly in data from the Solar and Heliospheric Observatory, SOHO, an aging spacecraft that has been staring at the sun for almost 30 years. The image came from its SWAN instrument, a hydrogen imager designed to map the solar wind. But this signal was different. The pattern of hydrogen emission wasn't solar. It was expanding outward, forming a cloud where no solar feature should exist. Within hours, Bezugly and his team realized they were looking at a comet, one so close to the sun that every ground-based telescope was blind to it. The object had already passed its closest approach to the sun before anyone even knew it existed. Designated C2025 R2 Swan, it instantly raised questions across the astronomy community. How could something this big, its hydrogen envelope stretching millions of miles, go unnoticed until it had already survived perihelion? Theories flooded in. Maybe it had approached from the far side of the sun. Maybe its orbit was unusually shallow. Maybe it had been dim until a sudden outburst. But none of those answers felt complete. The more data astronomers reviewed, the clearer the mystery became. This comet had entered our inner solar system through the one region where Earth's most powerful eyes simply cannot look. The sun's glare creates a no-go zone that astronomers have feared for over a century, a blind corridor extending roughly 30 degrees on either side of the solar disk. Inside this region, known as the Holochek effect, ground-based telescopes are effectively useless. The atmosphere scatters daylight, washing out any faint object, while geometry itself conspires against us. Anything approaching from the sun's direction is hidden until it swings wide enough into the darkness. Between late August and mid-September 2025, Swan moved directly through this invisible corridor. From Earth, it was buried in daylight, a massive, volatile body completely masked by the star it orbited. Only SOHO's ultraviolet eyes, tuned to hydrogen emissions invisible to human sight, could catch its presence. Without that data, the comet would have gone undetected until weeks after it had already left the inner system. That realization shook the scientific community. For decades, we've built billion-dollar observatories, from Pan-STARRS in Hawaii to the Vera Rubin Observatory in Chile, all of them blind in the same direction. And in that blind spot, a 100-kilometer-wide object passed silently. The early numbers made little sense. Swan's water production rate was off the charts, tens of thousands of pounds per second. Yet its nucleus remained unresolved, a single brilliant pixel surrounded by chaos. Models predicted it should have disintegrated near the sun, yet it didn't. Spectral readings showed erratic surges of cyanogen and C2 emissions, typical of comets in crisis. But Swan held together. Some scientists called it luck, a rare survivor of extreme heating. Others suspected a deeper irregularity, internal layering, rotation, maybe even a non-gravitational acceleration caused by asymmetric outgassing. The result was a moving target, drifting thousands of miles from its predicted orbit each day. And for researchers running planetary defense simulations, that was unnerving. The data didn't match any known pattern. Swan's path was stable enough to rule out danger, but unstable enough to hint at forces we still struggle to model. Each new image brought the same uneasy question. If an object this large can appear without warning, how many smaller ones slip past us every year, unseen, untracked, and waiting to surprise us? Right now, as you're watching this, C26 Orion E2025 R2 Swan is racing through the inner solar system. Its trajectory will bring it just 39 million kilometers from Earth, closer than Mars has been in years, and every major observatory on the planet is scrambling to capture data before the comet disappears back into the void for another 22,000 years. For NASA, ESA, and the handful of surviving space-based watchers, the next few nights are critical. Ground observatories in Chile, Hawaii, and South Africa are coordinating a 24-hour relay to track its rapidly shifting brightness. At the same time, NASA's NEOWISE telescope has been reoriented for emergency observation, and the James Webb Space Telescope has allocated a few precious minutes of infrared time, just enough to analyze the chemistry of Swan's coma before it moves out of range. But even with all that technology, the limitations are brutal. The comet's core remains unresolved, a glowing point wrapped in a fog of gas and dust. Its unpredictable jets distort the light curve, forcing constant recalculations of its orbit. Every hour, new images flood in, each one rewriting the last prediction. Inside the Jet Propulsion Laboratory in Pasadena, analysts are refreshing orbital fits in real time. The object's non-gravitational drift, a subtle push caused by outgassing, has already moved its predicted position by nearly 1,000 kilometers. That may sound small, but at cosmic scales, it's the difference between a clean miss and a planetary defense alert. Tonight matters because this is the window, the narrow slice of days, when humanity's instruments can actually see the comet clearly. Once it passes perihelion, Swan will fade rapidly, its surface cooling, its tail collapsing into a diffuse trail of dust. If we miss the chance now, the data is gone forever. What we learned tonight could redefine how we watch the skies. If Swan behaves as models predict, it will confirm that our warning systems still work, barely. But if it flares, fragments, or deviates again, it exposes a truth far more uncomfortable. Our planet's early warning network is balanced on luck, timing, and a few aging spacecraft keeping watch in the sun's shadow. Scientists now agree on one thing: Swan's behavior is unpredictable. But what happens next divides the community into three sharply different camps, each one painting a different picture of the coming week. The first scenario is the optimistic one, the safe case. In this version, C2025 R2 simply continues on its current path. It brightens modestly, reaches peak visibility around October 20th, then fades away as it heads back toward the outer system. In that timeline, the comet becomes a spectacular target for skywatchers, a bright green ghost gliding across the constellations, and a scientific windfall. Astronomers would have decades of data to model how large comets behave during near-Earth flybys. The world gets a cosmic show and nothing more. The second scenario is the unstable case. Swan's outgassing increases erratically, jets spin the nucleus faster, and thermal stress cracks its surface. Fragments begin to separate, maybe a few hundred meters wide each, invisible to most telescopes, but capable of producing their own dust and gas. This is how debris streams are born. In this case, Earth isn't in danger of impact, but our orbit may intersect Swan's residual trail in the months or years ahead. Even a diluted cloud of dust can boost micrometeoroid impacts on satellites, damaging solar arrays, eroding optics, or causing unexpected failures. It's the kind of slow-burn risk that never makes headlines, until something stops working. The third scenario is the one no one wants to consider. It's the extreme case. In this possibility, Swan's nucleus undergoes a structural collapse, either by internal pressure or a catastrophic outburst. Comet 73P Schwarzmann-Wachmann 3 did exactly that in 1995, fragmenting into dozens of pieces that plagued Earth's atmosphere with meteor storms for years. A similar event from Swan, so close to our orbit, could scatter a dense debris field through Earth's neighborhood. The odds of any direct strike remain minuscule, but the consequences for spacecraft and orbital infrastructure could be severe. Each scenario has precedent, each has historical analogs, and each depends on factors we still can't measure in real time: rotational spin, nucleus strength, subsurface ice distribution. The frustrating truth for planetary scientists is that no model fully predicts how a comet will behave once it begins to boil. For NASA's Planetary Defense Coordination Office, the task now is vigilance. Automated alerts update hourly, Amateur astronomers upload light curves to shared dashboards. The Minor Planet Center publishes daily orbital refinements. And yet, for all our algorithms and global coordination, the margin of surprise remains enormous. If SWAN survives intact, it becomes a triumph of science, proof that our detection network, even with blind spots, can adapt fast enough. But if it fragments, it exposes how fragile that system truly is. In every scenario, one fact remains. The difference between knowledge and chaos is measured in days, and the countdown is already running. In the long term, SWAN's brief visit is more than a spectacle. It's a stress test for the entire architecture of planetary defense. When something this massive can appear from the sun's direction unseen, it highlights a vulnerability that no technology on Earth has fully solved. Ground-based surveys like Pan-STARRS, Catalina, and the upcoming Vera Rubin Observatory dominate the search for asteroids and comets, but all of them share the same weakness. They can't look into sunlight. That blind wedge of sky, roughly 1/6 of the celestial sphere, remains a dead zone, even as thousands of satellites now orbit above it. In that zone, a long-period comet can cross the inner solar system completely unobserved. And while SWAN passed safely, its trajectory proves that a similar object could come much closer without warning. NASA and ESA have been planning to fix this. The Near-Earth Object Surveyor mission, scheduled for launch in the late 2020s, will scan the sky in infrared from a position far from Earth, mapping heat signatures that ground telescopes can't detect. But until that system is fully operational, our eyes on the sun-facing side of space depend on a handful of aging spacecraft. SOHO, launched in 1995, and the Solar Dynamics Observatory, already well past its design life. The SWAN discovery exposes how fragile that watch really is. A single malfunction, a lost calibration, or a delay in data review could mean missing the next one entirely. And the cost of missing isn't measured in impacts. It's measured in trust. The public believes NASA and ESA can see everything, that the sky is under control. SWAN reminds us that it isn't. Not yet. The broader consequences ripple far beyond astronomy. Insurance agencies that underwrite satellite fleets are already reviewing risk models. SpaceX and OneWeb, operating tens of thousands of low-orbit satellites, monitor micrometeoroid flux daily. Even a subtle increase in debris density can shorten operational lifetimes. A surge like SWAN's outburst, ejecting millions of tons of dust and gas into near-Earth space, could quietly change the environment we depend on for communication, navigation, and observation. But perhaps the deepest consequence isn't technological, it's philosophical. Each late discovery challenges our illusion of control. We build telescopes, algorithms, and predictive models, but the cosmos keeps reminding us that our systems see only what light allows. The unknown still rules the night sky, and sometimes, even daylight hides it. Behind every telescope feed and orbital diagram, there are people who haven't slept in days. In Pasadena, mission controllers sit in dim rooms surrounded by live telemetry streams, watching pixels flicker across outdated monitors. In Moscow and Paris, teams at ESA's Space Situational Awareness Center cross-check raw astrometry with volunteer uploads from backyard telescopes. And scattered across the world, thousands of amateur astronomers, people with modest telescopes and cheap tracking cameras, point their lenses toward the same faint smear of light that now bears the name SWAN. Each one knows they're chasing something ephemeral. A single dust flare can double the comet's brightness overnight, then vanish by dawn. Yet they keep watching, logging, refreshing data portals, hoping to be the first to spot a fragment or an unexpected turn. In online forums, they share notes, changes in tail length, fluctuations in magnitude, odd green tints from molecular emissions. The tone is urgent, collaborative, almost desperate, a global watchtower built from curiosity and insomnia. Inside NASA's Jet Propulsion Laboratory, one engineer described the mood as controlled chaos. Computers hum, coffee flows, and every few minutes someone mutters an update. New fits off by 900 kilometers. Outside, the world scrolls headlines about other things. Inside, they're holding together a chain of observation that keeps the rest of us informed. For them, this isn't just data. It's a fight against the dark, against the limits of what we can know before it's too late. When the final image packets from SOHO's Swan camera arrive each night, the first thing they check isn't brightness or trajectory, it's whether the feed is still alive. Because if that link goes silent, so does our early warning. And so, as C-2025R2 rushes toward its closest approach, it's the sleepless eyes of these engineers, scientists, and skywatchers who stand between mystery and awareness. They won't make front-page news, but without them, the next discovery might come too late. By the time you wake tomorrow, the comet Swan will already be receding, its bright coma dimming, its tail dissolving into the solar wind. The headlines may call it a close call, a scientific success, a celestial visitor that came and went, but the deeper story lingers. We saw it only because one aging spacecraft caught a shimmer of ultraviolet light that no one else was watching. One faint signal, buried in data, kept us from learning about it too late. That's the paradox of modern astronomy. The more we see, the more we realize how much remains invisible. For every atlas, for every swan, there are likely dozens, maybe hundreds of objects crossing the same skies, too faint, too close to the sun, too brief to catch. And each one is a reminder that our technological gaze, as powerful as it seems, is still just a flicker against the immensity of space. Swan won't strike Earth. It will leave quietly, on a 22,000-year loop that won't bring it back until every city, satellite, and civilization we know is gone. But its brief appearance exposes something lasting, a truth about perspective. The danger isn't always in what approaches us. Sometimes it's in what blinds us. So as we look up tonight, watching the faint green ghost of a comet sliding through the stars, the question isn't whether it's safe, it's whether we're ready to see the next one. Because somewhere, beyond that glare, another object is already inbound, hidden, silent, waiting for the right angle of light to reveal itself. And when it does, the world will once again turn its eyes upward, not just to marvel at what we've found, but to wonder, what else have we missed?